new 2x2 table. Okay, I'm going to move this out of the way. And I'm going to create a table where I'm examining two nominal variables, two nominal categorical variables. One of the variables is gender. Okay, so we know one value is going to be male, and the other value is going to be female. The other variable I'm going to look at is whether or not they recycle. Okay, yes, they recycle, or no, they don't recycle. Okay, simple enough, two values for each of these categorical variables. Okay, so now I'm going to create a table. And in this table, I'm going to work right in here. In this table, I'm going to examine gender as my exposure, right? So this is going to be male and this is going to be female. Okay, and I'm going to examine an outcome or a result. Okay, and that result is going to be whether or not they recycle. And this is going to be yes, they recycle, and no, they don't recycle. So in this crosstab or this table, in this box, I'm going to examine my sample population. I'm going to go out and I'm going to sample 100 people. And I'm going to go out and I'm going to examine these 100 people. I'm going to ask them their gender, and I'm going to ask them if they recycle. As it turns out, I may find that, say, 30 out of the 100 recycle, and 70 out of the 100 do not recycle. Okay, so now I need to figure out what I'm going to fill in here. Okay, so I'm saying to myself, okay, well, how many of these people were male and female? Well, let's see. Let's say that 60 were male and 40 were female. Okay, so let's see. That's our ratio of male to female, and I know 30 out of 70 in this population recycle. Well, let's say for a moment. Let me get this out of the way. Let's say for a moment that I don't know which of the 30 recyclers are male or female. All I know is that out of the entire population, 30 out of that 100 people, out of the entire sample I took, 30 out of that 100 people recycle. Okay, so what is my prevalence of recycling in this population? Okay, pretty easy, right? It's just going to be 30 over 100 is equal to 30%, 0.30. Okay, so now I'm going to ask you at this point now, well, if 30% of the population recycle, and this is this box is going to represent what I expect the outcome to be, right? My expected values. Well, what is my null hypothesis going to be? What would be a good null hypothesis going to be? Well, a good null hypothesis might be is that there's no relationship between gender and recycling. Okay, so now my alternative hypothesis is going to be that there is a relationship between gender and recycling. Well, let's start with our null hypothesis. This expected values table represents our null hypothesis. What we would expect to happen if there's no difference between the rates at which males recycle and the rates at which females recycle. Okay, so if I know overall in this population that 30% of the people recycle, how many males would I expect to be recyclers? In other words, what number of these 60 males would I expect to be in this box? Okay, I'm going to leave that up to you guys. What number do you think goes in there? Go on, needed opinion. 30% of the population recycles. We got 60 males. What percentage? If there's no difference between males and females, how many of those 60 do you expect to be recyclers? Somebody might want to hazard a guess. Come on. Leaving it up to me. Okay, 30 out of 60, 30% of 60 is going to be 18. Right? 0.3 times 60 is 18. Okay, so well, now you see how I got that 18? You guys get how I got that 18? 30% of the population is recyclers, right? That's a total number out of 100 that are recyclers, 30% of them recycle. 30% of the 60 males is 18. If it's true that 30% of the population recycles, we'd expect 30% of these 60 males to recycle. So that's going to be an 18. How about females? How many females will we expect to be recycled if there's 40 females in this sample? Let's have an opinion, right? It's also going to be 30%, right? Right, exactly, 12. All right, good. You got the idea. And you'll notice that this adds up to 30 as expected, because 30% of this goes in here, 30% of this goes in here, and overall 30% of the sum goes in here, is this total. Okay, so now if we have 18 males out of 60 that are recyclers, then we know what's going to be this value in here. It's got it, since there's 60 males, 18 of them recyclers, well, the remaining 42 males are not recyclers. And the remaining 28 females are not recyclers. And sure enough, if we add this together, we get the total of 70 people that don't recycle. Okay, so I just completed the table. In fact, just to show you something interesting, if I know the prevalence is 30%, and that I have 100 subjects, and this is 30, and this is 70, and I know that it's 60 males and 30 females. If I look at this, and if I know that this is 18, well, if I know that's 18, then this box has to be 12, right? Because it's got to add up to 30 people. It's 18 in here, and this going across here is a sum of 60. Well, this box has to add up to 42, and then finally down here, this has to add up to 28 in order for this to be 70 and for that to be 30, right? So did I make a mistake there? 40, I'm sorry, 40. So interestingly enough, once we knew one number, we could determine all of the others in this box. That's why we call this 1 degree of freedom. So we only have to know one value to determine all the rest of them. Okay, you know it by calculating the number of rows and number of columns, and the degrees of freedom for this particular table is equal to number of rows minus 1 times the number of columns minus 1. 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is equal to 1. So I get the same thing, 1 degree of freedom. Okay, now if we had a table that was 4 rows, or let's say 5 columns by 3 rows, 5 columns by 3 rows, the number of degrees of freedom there would be 5 columns minus 1 is 4, times 3 rows minus 1 is 2. 4 times 2, that's 8 degrees of freedom. Okay, that's going to be important to us when we go to our table to calculate our chi-square value. Okay, so this table represents our expected values. Okay, so now let's say I actually, this is what I would expect to find. Well, now I go back and I actually look at what the percentages, what the values really were. Okay, if I go and I sample 100 people in this population, right, I expect that, maybe I'll pull up Excel right now so that we can work with Excel, speed things up a little bit. Okay, over here I had that should be 70. Okay, now let's say in real life, I'm just going to fill in these numbers so we have exactly the same thing back here that we had here. Our expected values are 18, 42, 12, and 28. Well, let's say in reality, when I actually do this, this survey, that sure enough, I get 30 people who recycle and 70 people who don't recycle, out of a total of 100 people. And I say to myself, okay, well, let's say that instead of finding 18, I find that this is really 17 and 13. And this is really 41 and 29. Okay, would that be a very unusual result? In other words, if this is my expected values, would it, where 30% recycle and 70% do not recycle, Would I expect to get exactly 30% of the males recycling? Or might I see, just because it's a sample and not like the entire population, might I see, for instance, that in fact I might get 17 or I might get 20 or I may get so on and so forth, just by chance that the value is not exactly 30% because I'm going in to sample this whole thing. This table might represent my actual values or my observed values. Okay, my observed values are the ones that I actually find in the field, that I actually do a survey and the results that I get. Okay, well, in this particular example, I got, let's see, what did I get? I got 17, 41, 13, and 29, right? Not much different than the ones that I expected to get. So when I look at this, I say to myself, well, I'm so close to my expected values that it's hard for me to say that the null hypothesis is wrong, right? Because if I did it again, I might get 19 and 19 here and 44 here. If I did it another time, I might get 16 here and 39 here and so on and so forth. I'll very rarely get 100 people that I sample in a population where 30% recycle, that I'm going to get exactly my expected values. That's a pretty rare occurrence. Okay, but I should get something pretty close to that. Okay, now, if the values are much different, for instance, if I actually do this survey and I find that only 10 males out of 40 recycle, meaning 30 don't recycle, okay, or I'm using somewhat different numbers there, aren't I? I'll tell you what, let me match what I have there up on top. 60 and 40. 60 and 40. Okay, so let's say that I get observed values that look something like this. 10, let's see, if that's 10, this is going to be 50. And let's say here I got 20, and this is going to be 20, half the females in our sample recycled. These numbers are quite different from our expected values. So we have, it's important for us to know what's the probability of, if this null hypothesis is true, that there's no relationship between gender and recycling, what's the probability that I'll get something that's so different from what my expected values are? Okay, and the way that we calculate that is we calculate a function called ChiSquare, statistical function called ChiSquare. ChiSquare is pretty simple concept. Okay, we're going to calculate a statistic that says, I'm going to call it chi-square. Okay, and chi-square is going to be equal to what my observed value is minus my expected value. In other words, difference between this number, and I'm going to just fill this in here. This is 10 and 20. Okay, that leaves 60, 50, and 20. Okay, it's going to be the difference between, these are my observed values, these are my expected values. Okay, my observed values minus my expected value is going to be 18 minus 10, okay, which is going to be 8. Okay, now some of the what's going to happen now is that if I look at my second column, if I repeat that observed minus expected for this second value here, 42 minus 50, well, 42 minus 50 is going to be negative 8, right? So if I just take these numbers, the 8 from this cell, the difference in that cell, and add it to the difference in the next cell, they cancel each other out. I'm always going to wind up with 0. So in order to avoid that, I want to make this a positive number. So I'm going to take that observed minus expected value, and I'm going to square it. Okay, that makes it plus 8 times plus 8. For this case, it makes it minus 8 times minus 8 is going to be 64. It's going to be positive 64. Well, but that grossly inflates that number. So I'm going to take that next and divide it by the expected value for that cell, which is 18. So for each one of these cells, I'm going to examine the difference between the expected value and the observed value. I'm going to do it for this cell and this cell. I'm going to do it for this cell and this cell. I'm going to do it for this cell and this cell. I'm going to do this in Excel though. Okay, I'm going to take the observed value minus expected value squared, and I'm going to do it for each one of the cells, and I'm going to add all of those numbers together. That number, the bigger the differences are in each cell, the bigger my chi-square value is going to be, because I'm going to add those differences together. Bigger the differences, the bigger the this value observed minus expected over expected, squared over expected, and then when you wind up adding them all together, then you wind up with a larger number overall. Okay, so that chi-square value is going to be my statistic. I'm going to go to Excel, and I'm going to actually do this calculation. Okay, let me move this out of the way. Bring this in front. Okay, let's go ahead and do this calculation now. Okay, there's our observed values, there's our expected values, and let's see. My observed value is 10 minus my expected value. I'm going to square that value. I'm going to multiply it by itself. And I'm going to divide it by my expected value, by 18. Right? Okay, observed minus expected. Did I do that the right direction? Yes, I did. Okay, and I'm going to hit enter. So if I take 8, 10 minus 8, 10 minus, excuse me, 8, observed 10 minus 8 is negative 8, squared is plus 64, divided by my expected value, divided by 18. 64 divided by 18 is 3.55. Now I'm going to do the same thing for the next cell, which is going to be, let's see, it's going to be equal to, it's going to be, and I'm going to do this by hand now, it's going to be equal to, let's see, observed 50 minus 42, my expected, is 8, squared is 64, divided by my expected value, which is 42. So that's going to be 64 divided by 42. Okay, that comes out to 1.52. So now I'm going to repeat it for this cell, for the next cell. Let's see, observed value is 20, minus 12 is 8, squared is 64, divided by 12. 64 divided by 12 equals 64, divided by 12, and that's going to be the value in this column, in this cell. Okay, and finally, I'm going to take this cell, 20, my observed, minus my expected, 28 is 8, square that is 64, divided by the expected value 28. So that's going to be 64 divided by 28. You can just easily do this with a calculator, right? Okay, question was 10 minus 18. 10 minus 18 is observed minus expected is minus 8, right? Is minus 8. The squared is 64. Divided by 18. Are we okay with that? Right, 10 minus 18. Okay, good. You guys got that? Is everybody okay with that so far? Oh, okay. I wrote it right on the paper, but okay. I don't remember what I wrote before. Okay, good. I'm going to take the sum of it now. Equals sum. I'm going to add all these values together. Okay, and the total is going to be 12.69. Well, now, that value is my chi-square value. Okay, also symbolized as a chi. Chi is a capital chi is kind of, it looks like a capital X, script X. Chi-square value is going to be equal to 12.7, let's say, approximately. Well, remember I told you that the bigger the differences between my observed values and my expected values, the bigger this number is going to become when we actually calculate it. Well, now, what's the relationship of that to the differences, to the probability of getting this big a difference if there's no reason for a difference between the rate of male and female recycling? let's go back to here. Now, we have a probability table. There's a probability function and a a distribution that's associated with chi-square. Okay, and I'm going to just get a quick peek at that now. Okay, and what that's going to look like for 1 degree of freedom is going to be something like this. Okay, here's my chi-square value that I calculate. Gets bigger as I go to the right. And here is my probability of getting that outcome if there's no difference between males and females on their recycling rate, if the null hypothesis is true, in other words. Okay, well, I wouldn't expect it to be 0 because it's not real likely that I'm going to get exactly what my expected values are when I do a study like this. I'm always going to be a little bit off one way or another. So I'm going to start down here. And then as the number for chi-square, 1, 2, 3, 4, 1, 1, 2, 3, 4. Then as the chi-square value gets larger, well, the differences to get a chi-square value of 1 are a bit more than 0, but not real high yet. Probability of 2 is probably a bit more than that. But then as chi-square gets bigger, the probability of getting that outcome, if there's no difference between these two values, gets smaller and smaller. Okay, so now when I look at this distribution, what it tells me, and this is the chi-square value for 1 degree of freedom. Chi-square distribution for 5 degrees of freedom might look dramatically different, might be a much different shape. Okay, each one of these has its own distribution. Well, what this tells me is that the probability of getting a chi-square value bigger than 3 for one 2 by 2 table, getting a chi-square value bigger than 3 if there's no difference between the two exposures, between being male and female, between the genders in this case, is represented by this area here. Okay, it's more likely that you get a value that's less than 3 than a value more than 3. Well, if I go up even further, if I look at a value, what's the probability of getting a value as big as 5, chi-square value? Well, that probability of getting a value of 5, larger than 5, when the starting assumption is that there's no difference between one group and the other group in terms of the rate of recycling or the rate of disease, depending on what we're looking at, that probability gets smaller and smaller. So now, in order to reject the null hypothesis, we want a probability of being wrong, of when we say that they're different, we want a chi-square that's so big that the probability of it coming up when the null hypothesis is true, right? We want that probability to be very small so that we're less likely to be incorrect when we make that jump to rejecting the null hypothesis. Well, like most others, we often use alpha, our level of alpha error, being wrong if we reject the null hypothesis. We often make that set that at 5%. That's what I'm going to use now. As it happens, for 1 degree of freedom, right, the chi-square value that gives you exactly a 5% chance of being wrong, which leaves 5% at the end of this tail, 5% chance of the null hypothesis of this sample giving you a value that high if the null hypothesis is true. The probability, the value that has is 3.84. Any chi-square bigger than 3.84 leaves less than 5% chance of being wrong at the end of this tail. Okay, so I'm looking for, when I have 1 degree freedom, a chi-square value of 3.84 or larger before I reject the null hypothesis. So going back to my calculation, okay, my calculation says chi-square is equal to 12.7 with 1 degree of freedom. Do I accept or reject the null hypothesis that there's no difference in the rate that males recycle and females recycle? What do you guys think? Reject or accept? Okay, I got 1 accept. Any other opinions? I got one reject, one accept. Well, one of you has got to be wrong, right? Okay, so let's take a look at this. Now, the idea here is that the bigger the difference, so the null hypothesis is the null hypothesis is that there's no difference in the rate that males and females recycle. If that's true, we would expect small differences between the number of females and number of males that are recycling in our expected values and our observed values. We expect the difference in these numbers to be small. The difference in those, there's no, if the null hypothesis is true, we'd expect these differences, these cells that are based on the differences to be small also. And finally, for the chi-square value to be small. I know that if the chi-square value, my expectation is that if the null hypothesis is true, the chi-square value is not going to get bigger than 3.84. That's my critical value, right? Now we're all in agreement, right? We all see it, right? So this number, if this big number is bigger than my critical value for chi-square for that particular number of degrees of freedom, then I reject the null hypothesis, exactly. If this had come up to be, well, I'm sorry I didn't do this with the cell, so I could just go back and change the number. Let me give you a quick example so that you can see what happens when I do this. I'm going to copy this. Let me get a new table. Okay, let me zoom. Okay, if these differences had been small, if this had been 19 and this had been, okay, 19 would make this 43, and this would make this 21, and this would make this 70, this would be 27, right? I think that's right. Okay, my chi-square value here would be, let's see, observed minus expected is 1, right? Squared is 1, divided by my expected value is going to be 1 divided by 18. Okay, in this cell here, my observed is 21. Oops, did I make a mistake here? Yes, I did. That's going to be 11. That's going to be 11. And it's going to add up to, what did I do wrong here? 19. I really messed this up. 41. This is 11 and 29. I think I got it right now. Okay. So you're right, 11. Thank you. Okay. This is 19 minus 1. Okay. 11 minus 12 squared is 1. Divided by my expected value, that's going to be divided by 12. It's equal to 1 divided by 12. Okay, this is going to be equal to 41 minus 42 is 1. Squared is 1 divided by 42. 1 divided by 42. This is going to be equal to, let's see, this difference here is going to be 29 minus 28 is 1. 1 squared is 1 divided by 28 equals 1 divided by 28. Okay, when I add these together, my chi-square value is 0.19. Okay, now it's 1 degree of freedom. My critical value for chi-square for 1 degree of freedom was 3.84. Do I reject the null hypothesis or fail to reject the null hypothesis now? Opinions, please? Fail to reject, exactly, because this number is smaller than my chi-square value is. Okay, I failed to reject the null hypothesis. The differences between the observed and the expected are so small that they could be attributed to chance instead of a real difference between the rate at which males recycle and females recycle. Okay, so now I'm going to take this data again. I'm going to look at it another way. Well, first I want to show you a table. Okay, let me see if I can't find the chi-square table here. Z table. I'm going to have to do a quick search for it. Chi-square table. Let me see if I can't find it here. I should have one here. Square, where is it? Where is it? Where is it? Z table, T table. Press the. Nope. My goodness. Could have sworn I had one here. I'm just not looking in the right spot. Okay, I got one online. Okay, let's find some images here. Okay, this looks like a decent one here. Okay, hopefully you guys can see that. Oh, that's not the one I want, unfortunately. Let me find a better candidate. How about this? Okay, here we go. We're going to use this. Okay, so for 1 degree of freedom and a probability of being wrong if we reject the null hypothesis of 5%, our critical value of chi-square is 3.84, right? So if I exceed 3.84, I know my probability of being wrong is going down. See, as the number gets bigger, it goes down. If I want to be 99% certain, in other words, I want to have only 1% chance of being wrong if I reject the null hypothesis, my chi-square value has to be 6.84 or bigger. Okay, and if I want to be 99.9%, only have 1.1% chance of being wrong if I reject my null hypothesis, then my chi-square value has to be bigger than 10.83. In fact, in this particular example, our chi-square value was 12. So our chance of being wrong if we reject the null hypothesis is smaller than 1/10 of 1%, way smaller than 0.05. It's actually even smaller than 0.001 is our probability of being wrong. So you could even, if you wanted to be a little fancy, you could say, well, if I get a chi-square value of 5, I can say to myself, well, the probability of being wrong if I reject the null hypothesis is 5. Well, that's between these two chi-square values, 1 degree of freedom. So that means I'm somewhere between 5% and 1% chance of being wrong if I reject the null hypothesis. Okay, so you could use it that way. You could also do the same thing by going to Excel, and Excel has a chi-square value built in here. Chi-square dist, chi-square dot dist parentheses, and let's see. It asks for x. X is the value of chi-square, which I had before. It was about 12, comma, degrees of freedom is going to be 1, right? And I'm going to say, for cumulative, I'm going to say true. I'm going to close the parentheses and hit return. Okay, well, that gives me the probability to the left side of this chi-square distribution. If I go 1 minus that value, it gives me the area in the tail that's left. It gave me the area to the right. So the area in the tail that's left is indeed less than 0.001. It's 0.0005. That's my actual p-value or probability of being wrong. Now, if I showed you this table, okay, and I asked you, what is the critical value? How big does chi-square have to be for me to reject the null hypothesis with alpha equals 5% or 0.05 for 4 degrees of freedom? What would the value of chi-square have to be? Right? 4 degrees of freedom and 0.05. How big does chi-square have to be? Exactly right. Chi-square has to be 9.49 or larger before I can reject the null hypothesis that there's no difference in the rate of recycling among males and females, where there's no relationship between gender and recycling. Okay, good, excellent. Okay, so now I'm going to go back and we'll take a look at this data from another perspective. Okay, chi-square is actually pretty simple.